Welcome back. In this video, we'll explore a few examples to better understand the mechanics behind pulley systems. This is a continuation of my previous video, so if you haven't watched it yet, I highly recommend doing so to build a solid foundation of the concepts related to pulley systems. The link to the previous video is provided above. Alright, let's dive into this video and start with the first example. In this setup, we have two weightless pulleys, one fixed to a wooden bar and the other movable. A mass M1 is attached to the movable pulley, and a weightless, inextensible rope passes around the pulleys. One end of the rope is connected to a mass M2, which is heavier than M1, while the other end is tied to the fixed pulley. When the system is released and allowed to free fall, we need to determine the acceleration of both masses. Let's start by assuming that mass M1 is moving upward with an acceleration A1, while mass M2 is moving downward with an acceleration A2. The tension in the rope, which we'll denote as T, is uniform throughout its length since the rope is both weightless and inextensible. To begin, let's look at the free body diagrams for the movable pulley and the mass M2. Using these diagrams, we'll apply Newton's second law separately to each system to analyze their motion. The movable pulley is supported by two segments of the rope, while mass M2 is connected to one segment. Since the tension in the rope is uniform throughout its length, we can represent the upward forces acting on both systems accordingly, as shown in the diagram. The weights and accelerations of the two masses can also be indicated in the diagram. Here, G represents the gravitational acceleration. We do not necessarily need to identify the directions of the accelerations explicitly beforehand. Once we solve for the acceleration, the solution will naturally reveal the correct direction of motion. We will first apply Newton's second law to the movable pulley system, considering the direction of acceleration. Then, we will apply it to the second system, again accounting for the direction of acceleration. By eliminating the tension from these two equations, we can derive an expression that relates the accelerations of the two masses. To determine the two accelerations, we require an additional expression that links them. In this pulley system, the motion of the masses is inherently interconnected by the constraints of the rope. If one mass moves a certain distance, the other mass moves proportionally to maintain the rope's tension and ensure continuous motion. This relationship provides the second equation necessary to solve for the accelerations of both masses. For instance, if the movable pulley, along with mass M1, moves a distance of h meters in time t, the mass M2 moves 2h meters in the same time. This is due to the rope segments supporting the movable pulley, which adjust their lengths proportionally, causing M2 to move at twice the rate of the movable pulley. This relationship ties the displacements and consequently the accelerations of the two masses, which means the acceleration of mass M2 is twice that of mass M1. Please check my previous video where I explained how to determine distances in pulley systems using the principle of energy conservation. We can substitute the expression for A sub 2 into equation 3 above to derive the formula for the acceleration of mass M1. Since the acceleration of mass M2 is twice that of mass M1, we can calculate it as well. This relationship directly follows from the constraints imposed by the pulley system. Also, note that the weight of mass M2 is greater than that of mass M1. Consequently, the expressions for both accelerations are positive, validating that the initial directions of acceleration we identified are correct. We can follow this approach only if the movements of each pulley and weight relative to the others are known. However, if these constraints are not specified, a more general method is required, one that can be universally applied to any type of pulley system, to determine the relationship between the accelerations of the weights within the system. We will first express the coordinates of each component of the system from a reference plane and express the total length of the rope in terms of these coordinates. This involves leveraging the constraint condition of the pulley system, where the constant length of the rope is represented using the coordinates of the objects. This relationship will form the basis for calculating the acceleration of the objects in the pulley system. Let's establish a reference plane, or datum, for our measurements. We'll choose a point near the fixed pulley as our reference. The length of the section of the rope passing over the fixed pulley remains constant even as the rope slides over the pulley. Let's denote this fixed section of the rope as S sub 1. Similarly, the length of the section of the rope under the movable pulley is also constant, regardless of the movement of the pulley. Let's denote this fixed section as S sub 2. We are now left with two objects for which we need to define coordinates: the movable pulley, along with mass m sub 1, and mass m sub 2. For simplicity, I am treating the movable pulley and mass m sub 1 as a single unit. However, if preferred, we could consider the weight m sub 1 and the movable pulley independently. It will not affect the final result. Returning to the task of defining the coordinates, we know that the displacements of these two objects are interconnected. Nevertheless, we will treat them separately and denote their distances from the chosen datum as h sub 1 and h sub 2, respectively. It's important to note that these coordinates change with time, unlike s sub 1 and s sub 2. For clarity, the distances measured from the datum to mass m2 and the movable pulley are taken in the positive direction. With that said, we can now write an expression for the total length of the rope, L, in terms of the subcomponents of S and H. Now, why do we need to write this expression for the length of the rope? The purpose is to establish a relationship between the acceleration of mass m2 and the acceleration of the movable pulley. In a pulley system, the length of the rope is fixed, assuming it is inextensible. This means that when one part of the system moves, other parts must move in a way that satisfies this fixed length. This relationship is referred to as the constraint equation. Constraint equations are crucial for solving pulley system problems because they establish the relationships between the displacements, velocities, and accelerations of the system's components. These relationships stem from the physical constraints imposed by the inextensible rope and the geometry of the pulley system. In a pulley system, referencing all measurements to a single fixed datum is crucial for consistency when analyzing forces, displacements, or velocities. This ensures that the relative motion of the different parts of the system is properly accounted for, avoiding confusion or errors in calculations. Now, we need to determine the rate of change of these lengths. Since the total length of the rope remains constant, the rate of change of the total rope length is 0. Similarly, the lengths S1 and S2 do not vary with time, so their rates of change are also 0. This leaves us with H1 and H2, which do change with time. The change in length or displacement over time is defined as velocity. Thus, we can derive a constraint equation that relates the velocities of the moving components within the system. This is in essence taking the derivative of the constraint equation with respect to time. Next, we'll determine the rate of change of velocity, which corresponds to the acceleration of the two objects. Since both velocities change with time, we can derive the constraint equation for acceleration by differentiating the velocity constraint equation. This step reveals the relationships between the accelerations of the moving components in the pulley system, ensuring that the constraints imposed by the rope are maintained. Remember, when we defined the datum, we decided that all downward measurements would be positive. However, since the acceleration A1 is directed upward, it is assigned a negative sign. Let's clear the screen and make space for calculating the acceleration. All that's left is to substitute the expression for A2 into the third equation to determine the acceleration A1. Once we have determined the acceleration A1, we can easily calculate the acceleration A2, which is twice that of A1. There's no difference in the values obtained using either approach. However, using the constraint equation is a more systematic method and can be universally applied to any pulley system. Just ensure that all measurements are consistently taken from the same datum, even when dealing with multiple ropes. The next example we explore will provide a much clearer understanding of the concepts we've covered so far. Before we continue, I'd like to kindly ask you to give this video a thumbs up, subscribe to the channel, and hit the notification bell so you don't miss any updates. Your support truly means a lot. Thank you. Now, let's get back to the video. Let's consider a scenario with two pulleys, one fixed and the other movable. Both pulleys, as well as the ropes, are considered weightless and frictionless. On one end of the rope, passing over the fixed pulley, hangs a 10 kilograms mass, while the other end is connected to the movable pulley. The movable pulley holds two masses, 4 kilograms and 2 kilograms, suspended on opposite ends of the rope running over it. The task is to determine the acceleration of all three masses and the tension in each rope when the system is released from rest. We will identify the tension in the rope passing over the fixed pulley as T1 and the tension in the rope passing over the movable pulley as T2. Remember, the tension on either side of the rope is identical because both the rope and pulley are weightless and there is no friction between them. However, if the pulley or rope had weight or if friction were present, the tension would vary along the rope. I'll leave that topic for another discussion. As the first step in finding the accelerations and tensions, let's establish a reference point for measurements within the pulley system. Choosing a stationary point ensures that all measurements of length, displacement, velocity, and acceleration are consistently defined relative to this fixed frame of reference. By establishing a reference point, also known as a datum, you create a consistent frame of reference for applying constraints and analyzing motion. When dealing with multiple pulleys or ropes, the topmost fixed pulley is a natural choice, as it simplifies writing the constraint equations. This approach ensures uniformity in problem solving, since the topmost fixed pulley is common to the entire system. It is not mandatory to choose this point. You can select any fixed point in the system as your datum. However, choosing the topmost pulley is a standard practice for convenience. Other choices may complicate the analysis, requiring additional steps to redefine displacements or modify constraint equations. In this example, we will position the datum at the axis of the fixed pulley. Measurements taken downward, away from the datum, will be considered positive, while measurements taken upward, towards the datum, will be considered negative. Next, we will assume that the accelerations of all the weights are in the positive direction and label them accordingly. Any negative values in the solution will naturally indicate motion in the opposite direction. To determine the accelerations of the system, we apply Newton's second law of motion to each mass in the direction of its respective acceleration. Starting with the 10 kilogram mass, the forces acting on it are its weight 10g and the upward tension in the rope, T1. Using Newton's second law, the net force is 10g minus T1 equals 10 times A1, where g is the gravitational acceleration and A1 is the acceleration of the 10 kilogram mass. Next, we apply Newton's second law to the 4 kilogram and 2 kilogram masses, considering their respective directions of acceleration. For the 4 kilogram mass, let the tension in its rope segment be T2. The forces acting are the upward tension T2 and the downward weight 4g, giving 4g minus T2 equals 4 times A2. For the 2 kilogram mass, the forces include the upward tension in its rope segment T2 and its downward weight 2g. Newton's second law gives 2g minus T2 equals 2 times A3. For a movable pulley supported by two rope segments, the tension in each segment T2 is identical, as the rope is massless and continuous. Consequently, the total upward force on the pulley T1 is the sum of the tensions in the two segments, resulting in T1 equals 2 times T2. This relationship ensures equilibrium for the massless pulley, where the upward force T1 precisely balances the downward force acting on the pulley. We have now arrived at the final step of deriving the constraint equations for the system by analyzing the lengths of the two ropes. Starting with the fixed pulley, let the total length of the rope passing over it be L1, which remains constant throughout the motion. A portion of this rope, denoted as S1, is fixed and does not vary with the movement of the masses. However, the remaining sections, represented by H1 and H sub x, vary with time as the masses and the movable pulley shift positions. It is essential to take all measurements for the movable objects from a single reference point, which in this case is identified as the datum. Using a single, consistent datum ensures clarity and accuracy when deriving constraint equations. Having multiple reference points within the same system would create inconsistencies and complicate the analysis, making it impossible to relate the displacements of different components effectively. With that established, let us now express the total length of the rope in terms of the identified distances. Using the datum as the reference point, the total length of the rope can be written as the sum of the fixed portion, S1, and the variable portions, H1 and Hx, that change with the movement of the masses. Thus, the total rope length is L1 equals S1 plus H1 Hx. This equation relates the constant and variable segments of the rope, laying the foundation for deriving the constraint equations. Similarly, we can express the total length of the second rope, L2, which passes over the movable pulley, as L2 equals S2 plus H2 prime plus H3 prime. In this case, S2 represents the fixed portion of the rope that does not change with the motion of the masses, while H2 prime and H3 prime are the variable portions that change with time as the masses move. This expression is analogous to the first rope and helps establish the relationship between the fixed and variable sections for the second pulley system. To establish the distances from the datum to the 4 kg mass and the 2 kg mass, let us define the distances from the datum to each mass as H2 and H3, respectively. Additionally, the section between the top of the movable pulley and the center of the pulley will be denoted as Sx, which is a fixed length. To ensure all measurements are taken from a single reference point, the datum, we replace H2 prime and H3 prime with H2 and H3 respectively. Considering the geometry of the ropes and the weights, we can express the relationships as follows. H2 prime equals H2 minus Hx minus Sx. Here, H2 is the distance from the datum to the 4 kg mass. Hx is the vertical distance from the datum to the top of the movable pulley, and Sx is the fixed length from the top of the movable pulley to its center. This equation adjusts H2 prime, the length of the variable rope segment, related to the 4 kg mass, to be consistent with measurements from the datum. Similarly, we can write an expression for H3 prime as H3 prime equals H3 minus Hx minus Sx. Here, H3 is the distance from the datum to the 2 kg mass. Using the expressions for H2 prime and H3 prime, we can now rewrite the total length of the second rope, L2, as follows. This is the simplified expression for L2, with all varying measurements taken from the datum, consistent with the system's geometry. Since we are interested in the accelerations of the three weights rather than the distances from the datum, we proceed by taking the second derivative of the expressions for L1 and L2. The fixed lengths, L and S, subscripts, remain constant over time, meaning their derivatives are zero. As a result, when the expressions are differentiated twice with respect to time, only the second-order derivatives of H1, H2, H3, and Hx remain. By taking the second derivative of H1, H2, H3, and Hx with respect to time, we obtain the accelerations of the respective masses and the movable pulley. This follows from the fact that the second derivative of position with respect to time represents acceleration. The resulting accelerations are A1, A2, A3, and Ax, which correspond to the accelerations of the 10 kg mass, the 4 kg mass, the 2 kg mass, and the movable pulley. It's important to note that the direction of displacement should align with the direction of acceleration. When taking the second derivative of the position with respect to time, the resulting acceleration must be in the same direction as the displacement for consistency. For example, If we define downward as the positive direction for displacement and acceleration, then the acceleration for each mass must be considered with respect to this reference. If the displacement is upward, the acceleration would have a negative value in that direction. Ensuring this alignment between displacement and acceleration ensures the correct directionality of the accelerations in the system. The acceleration ax is essentially the additive inverse of a1. Therefore, in equation B, we can replace ax with minus a1. This substitution not only simplifies the equation by eliminating ax, but also expresses the relationship between the accelerations directly in terms of a1, a2, and a3. This is due to the constraints imposed by the ropes in a pulley system. We can express a1, a2, and a3 in terms of t1 and t2 as follows. By substituting these expressions for accelerations into equation 5, we obtain an equation that involves only the tensions t1 and t2. Since T1 is known to be twice T2, based on the relationship derived from the movable pulley system, we can substitute this relationship into the equation. This substitution simplifies the equation, allowing us to solve for the value of T2. From the calculations, T2 is determined to be 34.12 newtons. Once T2 is determined, T1 can be calculated as twice T2. This gives T1 as 68.24 newtons. These values of T1 and T2 can be substituted back into the acceleration equations to calculate the accelerations of the three masses in the system. The 10 kilogram mass accelerates at a rate of 2.98 meters per second squared. The acceleration of the 4 kilogram mass is 1.28 meters per second squared, while the 2 kilogram mass has an acceleration of negative 7.25 meters per second squared. The negative sign indicates that the 2 kilogram mass moves upward, whereas the other two masses move downward. This outcome aligns with the constraints imposed by the ropes, as the total length of the ropes must remain constant throughout the system's motion. And with that, we've come to the end of this video. I truly hope you've gained valuable insights that you can apply in your own learning journey. Your feedback is incredibly important to me. Let me know what you think about the videos on my channel. Your thoughts will guide me in improving and bringing even more relevant content your way. If you haven't subscribed yet, make sure to hit that subscribe button before you leave. A big thank you to all of you who have already subscribed. I appreciate your support more than you know. Until we meet again in the next video, take care, stay curious, and goodbye.